I also happen to be a physicist. So I did my doctorate in physics, and I am always very proud of that because I always say physics is the mother of science. From that spread so many things. So basically, that is why, with that happy note, I would like to address you and give some my knowledge, whatever my experience, which I gained through working in Indian Meteorological Department for about 6 years, and further in the ISRO for about 35 years. So let us just start with the basic thing. Why a technology like space? A technology like space very why a poor country like India should take up that? There is one basic question which anybody would ask when the space started its activities. I will try to answer that question through my thought. At the end of the thing, we can conclude how good it has been happening and how it has helped our country. So basically, you can see here in my first slide a few things. Starting from the ground, some systems, and we go to the rocket, we go to the computer, then finally to the moon or any other, planets and satellites. Basically, all these have become now integrated part of the human living. So let us see how these things have happened. We'll go to the next slide.
Next slide, Raman.
Ramanji, next slide. Yeah. See, basically, how all these things started is around 1972-73. We got our independence, and science departments were being developed. There was no space department at that time. And there's a youngster like Vikram Sarabhai. He's a revolutionary visionary. He used to think about 100 years ahead, actually, I should say. See, he only developed our Indian Institute of Management, IIM. First IIM in Ahmedabad was set up by him with his money, with his land, everything his. Nothing the government has to do with that. And you know now how primary institution it is. It is as good as any institution of that kind in the whole world. So with that idea, he had happened to go to the USA. There they were discussing at that time, 1970s, discussing about satellites, how it can be used for communication or imaging or some other studies and all that. He was very much attracted by that because basically back home in India, we don't have any good map. We don't have any communication. Many of the villages don't have electricity. There is no connectivity at all. So he thought that this technology, even though it is very high-end technology, maybe a little costly also, can solve many of the problems of the country. This was his visionary idea. And with that idea, he came back and he talked to Nehru. Pandit Jawaharlal Nehru was for Prime Minister at that time, and got some little money to develop the systems, develop a sort of rocket and all. The starting point and basic starting point for any space program is how to go to space. Now let me just define what is space. You know very well our Earth is surrounded by an atmosphere, and there are many planets and where no atmosphere also is there. For example, if you go to the moon, there is no atmosphere there. Straight away, the land and the sun space. So where the atmosphere ends, there starts the space. So you are actually going outside our own system, the Earth and the atmosphere. Once you go outside that 100, 200, 500 kilometers up, you are actually into the space. And what we found is, the more and more you go to the space, you get a better and better view of our Earth. For example, there was systems like Aristotle and all that, much long back. They were arguing that it's a square. It's a square. I can just walk and go anywhere. It's plain. I'm not seeing any spherical nature. Yes, satellites proved that to be wrong. First time with actual proof. A round thing in the space. That is what our Earth is. That is what any planet is actually. So basically, these things can happen only when you go away and away in the space. This is one of the important things. Second thing is, in space there is no gravity, no weight, no gravity, and no pollutants, no such effects. So basically, it's a very good place to study the Earth and other systems. Next slide. Next slide, sir.
Next slide.
Yeah. Okay, what's the basic principle? We are all physics people. Basic principle is what Kepler did. Johannes Kepler, such a wonderful person, day and night, Galileo has worked. Actually, Galileo only discovered the telescope. He was so fond of that, he used to forget even taking food, go to sleep and nothing. All through the night, he was actually measuring the different positions of the basic stars, important stars, planets, everything. And he used to draw actually in a spherical sheet. The spherical sheet he formed and used to. But what Johannes Kepler did, he used all of them, measured the distances, giving some unit actually at that time. Nobody knows how much is the distance of different stars and all. He gave a unit, and when he worked out, to his surprise, he found any object which is moving around another object will be in an elliptical orbit. Let us not confuse that under attractive force, under the gravitational force. No other thing. Like our fan is rotating around, no, it is not going in elliptical orbit. It's a centralized point. Whereas any two objects, they influence each other. So both of them are moving because of that elliptical orbit. This is number one. Number two, they are sweeping out equal areas. Then when they come to the elliptical, that far end actually, apogee, they move fast. Perigee, they move slow. Like that. That I take care. You can adjust for that. Because of this, there's a relationship of between the time period and the radius. So all these things are what we are using actually. Mathematics, the mathematics part of the space is actually, we have to calculate all these things before sending a satellite. Its weight and all that comes later, but where we want to send it, at what speed it should go, all these are decided by these equations, Kepler's equations. Next one. So basically, basic equations are to be used, and up to the level of about third, fourth decimals. If you make a small mistake, for example, I am launching a satellite which has to go to the moon. You can see the Earth is rotating, moving. That particular satellite is moving, moon also is moving. The whole system, in a moving system, I am sending something. By the time it travels, let us say 3 days, 4 days, moon has to be there. So I have to calculate according to such a way that the moon comes exactly around that period and our satellite gets into that orbit. I will explain with some other figures a little later. So what are the different types of satellite orbits we can think of? One basic thing we can think of is actually something which goes around. That is called as the polar orbit. Around the poles or around anything. Anywhere. Polar orbit we simply call, it can be around any other axis also. But anything going around that, it will have a fixed period of about 80 minutes. 80 minutes, one round it will make, and the Earth also is rotating. So we can see that about 22 days. Once in 22 days, it will again come back. For example, today one satellite, IRS satellite, has come over Bangalore. Again, it has to come means another 22 days it will take. That is why we have got a multiplication of satellites. 4 to 5 satellites, 22 divided by 5 means 4 days. So at least 4 to 5 days you have to watch that area. Then only you can talk about crop, you can talk about plantations, forest, any dynamic aspects like water bodies. All those things you can study only with at least minimum of 3 to 4 periodicity. That's why we are having a number of satellites. Some people will think one satellite is enough. See why you are having so many satellites and wasting the time, wasting the money. No. These 3-4 satellites will assure that I get data every 3 to 4 days. This is one type of orbit, one which is below, you can see here, polar orbit. Another one is equatorial orbit. This is a very interesting thing. The satellite should have the same time period, 23 minutes, 59 seconds, like that, 59 minutes and like that, 23 hours, almost 24 hours you can say, one day. That means when the Earth is rotating one day, one round, satellite also is rotating. So what it means, like you are going in a bus, another bus is coming, same speed, you will be able to see everybody inside. You are actually moving, but you are actually stationary also. Like that. This satellite will be always in the same position, interestingly. And this type of satellites are required for communication, weather, disaster management. Some of these things which you don't want to go here and there, try to find data. Same place, you have to keep on watching. Even defense, security, and our ocean security, all those things. I'll explain those things, some examples a little later. So this is a very important satellite. That is equatorial satellite, but very difficult to launch because the distance of the satellite from the Earth is 23,000 kilometers. That far I have to launch. My power of the launching should be that much. Whereas a polar orbit I can launch from 500 kilometers to 1,000 kilometers. 500,000 can be a polar orbiting. Whereas equatorial orbit, I have to go up to 23,600 to be very clear. That much distance I have to go. Then a third one is there. A satellite which is at any other inclination. Not equatorial, little away from there. So what will happen is, in a day, 2 times it will come and see the same place. These are required for cyclone monitoring and all that. Cyclone monitoring every day I want to see 2-3 times. So that is called a not exactly equatorial, not exactly polar orbit, in between orbit, but very rare. They are all not much actually. Basically, our satellites are in the polar or equatorial orbit only. Next one. But all this I am telling in a very simple way, but to do the calculations and send it properly, that is where the accuracy lies. Many of the satellites fail because of other countries, they fail because mathematics part has not been done properly and it goes off the orbit. Then it's of no use. You will not get any good data. Whereas India has a very good record of mathematical calculations. That is called orbital mechanics. There's a big group in space applications here actually in ISRO Satellite Center, now called as Professor U. Rao Center in Bangalore, which has got, they do calculation even for other countries also. See, we get money for that. Suppose I plan their satellite and this is how you have to launch, this is the time it will take, then they give money to us. We do the work for them also. Now you can see what is the evolution of satellites in the world itself. Around the world, 57 Russians, thing called Sputnik. One failed actually, Sputnik 2. You can see here, 57. Then further things moved, and there is a satellite like Echo. That's the first meteorological satellite, which came was in 1960, which took some cloud pictures and all that. It was the first satellite we launched in the orbit. Next one. Next slide, sir. Satellite launching. Now, I'll tell you the complication of the whole thing. You can make all these systems very well. Camera you can make the container, you can make the cooling system, you can make the data transfer also is there. I take pictures, I convert that into digital data and I have to get in the earth. Then only I can process it further. So to do all those things, I got capability, let us say. In the earth, I am doing all this in a laboratory, there's no problem. But what about the launching? It's going to happen in space and I have to communicate with them. See, suppose I am going sending something to the moon, is about more than 2 lakhs, 1.75 lakh kilometers. That far, my signal has to go, and the signal coming from there I have to receive, and I have to talk to the system, satellite. That is where the communication also has to improve, and I will show you that how it has improved. So this is the launching. You can see here, basically, any satellite launcher will have one big thing, one big tall structure. That's a basic main firing system. And around that, there are 2 more. Some may have 4 also. This for balancing part. See, you can think of this, even a 1 degree, half degree change in its straightforwardness, verticality, it will go and land somewhere else, isn't it? See, unless you are very perfectly vertical, it can actually go away. So for that only, to control that only, there are 2 separate, on the both sides, there are separate small boosters, they call booster rockets are there. The main rocket may have 3 levels also. Level 1, level 2, level 3. Now what we are doing, we are actually trying to do away with those also. Straight away 1 level only. So no more firing at the first level over, second level and all these things. No complication. Straight away 1 firing you do and then control these things. Now what is this principle of this launching? You all know very well, it is Newton's law. Third law, action, reaction. That is, whenever I am putting a thrust downwards, the whole satellite goes up. And what is the thruster actually? Here it's explosion. Explosive material like hydrogen, oxygen, or a mix of all these things. I have to carefully keep it there so that when the explosion is taking place, the remaining material should not get exploded actually. Okay? This is one thing, very important. Second thing, as it is going and going, the fuel is getting depleted and the weight of the fuel is reducing. So this is actually an accelerated system. This is not like our bus and all that same weight. F equal to ma, I cannot use it. F is equal to ma plus dm, that also will come. Because change of mass also is happening here. So that is again a big computation is there. With the same thrust, it may go much faster also. So I have to control the thruster. So for that, there are controlling systems. So basically, I want to tell you, in a launch like this, about 16 computers will be there inside. 16 computers. For each of them, the flow, other things, temperature, everything is being measured. That is what you see during the launch. You will see people are sitting in different screens, and each of them are looking at the critical values. If anything changes, they have to control it. Don't think it's all lost. No. When something changes, that immediately cool. For example, temperature increases, that do the cooling. So all these are done online straight away. And as the satellite is going, its height is seen, altitude we call, and range also. From our station, how much far away it has gone. And in addition to all these things, safety and security of the ships which are there below in the ocean, and countries also. By mistake, if you put a satellite, goes to some other country, it's like war on it. So basically, you have to destroy it. Destroy your means such satellite, there is button actually separately. You just press and the whole thing gets burst in the atmosphere. Nothing go and hit some country. But in India, luckily, we have got such a safety record. No time we have done any of those type of things. Interesting. Most of the satellites have been all successful only, totally. But the basic thing is how to control that explosion, and that is where the hydrodynamics and very complicated equations come. What's the speed of that fuel? What's the burning? How much explosion to take place? What should be thrust? All these have been calculated. Accordingly, these things work. Now we have got two satellite launches, polar and this one. Both things are global also. It can go up to the geopolar also. Up to the height of 23,000 it can reach. The other one can reach up to 800 kilometers. Next one. Now we are doing launching for other countries also. There's a lot of money we get from that also. Now you can see here quickly, there are so many satellites, I have not put all of them. The simple ones, for example, Aryabhatta. You can see, we used to call it as tiffin box satellite, tiffin box. Exactly a big tiffin box, of course, not small one. That was a type. And you can see here, all around there is this one, solar panels. Because one important thing you have to see here, any satellite, once you go to the space, we cannot provide any material to it. Only we can communicate with it, control something. But we cannot give any power, we cannot give any cooling, nothing we can do. Everything has to be done by satellite only. It's an automated system. So there, energy has to be there. Solar energy is the energy which we use, and highly efficient solar energy. So here throughout the satellite, you can see here. Then we moved further down, you can see like wings. We are having like wings, which are the solar panels. And these panels, I can tell you just roughly, whichever room you are sitting now, is that size actually. Don't think they are very small like that. Because in space, what happens? There is no weight. See, if you go to the space, your weight is zero. Some people I used to tell, they want to reduce their weight. Go to space. Just for fun, I am telling. So basically what happens, the solar panels are so big, but their weight has no meaning for the satellite. It's not carrying it. The weight is zero actually. But that can generate lots of power. Kilowatt power it can generate, and continuously. Except during the eclipse. Eclipse time, what they do? They fold it. They stop the operation. Because eclipse time, there will be no power and it should not be operated. Otherwise, they are continuing operating. So now we can see up to the Aditya. The recent Aditya is actually what? A satellite which has gone up to very closest to the sun, one equinox point they call. Closest to the sun one can go, one has gone. Nobody has gone more than that. But you just think about the satellite. What will be the heat it will be getting? What will be the different high power cosmic rays and other things getting? So basically, a lot of material science we have to do in ISRO to develop that materials. There is a big group in Trivandrum, BSSC, material science group. They are doing actually different materials which can withstand high temperature, very high. And they are all basically, you can say like porcelain, no, stone and all. They can withstand many be high. So that type of materials are used, research, but their weight should be less also. So initial launching should not be very heavy. Afterwards, weight has no meaning. But initial launching has to be careful. So with that things, Aditya has been made successful. Now he's taking a lot of measurements. And then Chandrayaan, 1, 2, 3. And it's a proud moment for all Indians, all of us, that soft landed. See, nobody, even Japanese, afterwards they send something, and they don't know for 3 to 4 days whether it has landed or not. Afterwards they got signal. Now I think they are getting signal. So that their rover has landed. Whereas our rover landed, started operating, 15 days it operated. Then dark period comes, 15 days, sun, moon will be bright, then moon will be dark. The dark period cannot generate power. So we'll find out some method to do that also in the next one. But basically, any landing in the moon is very difficult because moon is full of rocks and big trenches, then big mountains, and there, if you see their gravitational field, it is continuously varying. Every 10 minutes, 15 meters is varying. In such a place, anything cannot land. So we have to actually, first what we did, we formed a gravitometer we developed, and that was measuring the gravity. And when we found a plain place where gravity is almost same, there it landed. That's the success of the landing. And all countries are appreciating that because this is a science method, the new method itself we have found out how to land in a very tough terrain like that with a lot of gravitational changes. Next slide. Next, sir. Yeah. See here, there are basically you can three types of satellites. We can actually divide that into. One is actually the satellites which will be giving communication. The first one goes up to geostationary orbit. Second one IRS, remote sensing satellite. Third one is satellites like Aditya and all, space satellites, which are going to the space. We are actually going it away from our Earth system itself. It's going. Next one. Next slide. Now here you can see the complication. See, you see a very simple thing, 1979 what we did, 2019 what we did. You just see it. This is one of the state-of-the-art satellites, Cartosat 2, which can give accuracy of 1 meter. Anything 1 meter it can actually see. I will show some picture also. Over the earth, every house, every road, every tree, everything it can map. You just think of the mapping capability because we are at about 800, 900 kilometers. From there, what type of signal it will get from the earth? You can think of that. So what type of powerful cameras it should have to map such things. So this technology itself is different. It is not normal cameras which you do to photograph. I cannot photograph more than maximum 10 kilometers, isn't it? A mountain is there, I can photograph, that's all. Whereas these are not that type of camera. These are working on the principle of photoelectricity. What Einstein discovered and got Nobel Prize for that. Photoelectricity is being used. Even one photon, if you can catch, gets the image. So that is a method we use. That is why we are able to go up to the 1 meter or sub-meter levels and all that. So the technology development, all this, even a screw and nut has not been given by any country. Let me very proudly tell that. Because nobody will give also to India, because they know our capability. We can convert that into much bigger things. So nothing was sold to us. We have to develop everything. So a big technology jump only what India and ISRO has done. Independently, indigenously, our people have done this. From that type of satellite, now this ocean sat, people are buying our data. There's another ocean sat also is there, similar to this. They buy data from us because over the ocean there is no data, no satellite. So we are selling them, getting a lot of money from that also. Next one. Next slide, sir. Okay, let me go a little faster, okay? So communication, you know very well how important is communication and how poor it was in India. See, I remember myself when I joined ISRO, that is in 84, I had to travel sometime abroad also. See, make a phone call, I had to go to that particular place, my hotel, then book for that, then the trunk call, they will connect, and almost half a day. Now, from USA, in WhatsApp I can talk to you, just now. This talk I can give in WhatsApp from USA. Think of the technology jump that has happened, communication, only due to the satellite. Because with the towers and all, you could have never done it. You could have had at least 1 million towers are required then. And over the ocean also. Then only you can talk, otherwise not possible. Now all these aeroplanes also, long distance plane, they are giving Wi-Fi. You can talk from the plane, you can talk to your people. It has come to that level. Even there also satellite connectivity is there. Satellite, what happens, when being in that central place, it can receive all signals and send it. And every satellite is equivalent to about 1,000 telephone exchanges. You have seen telephone exchange, In Bangalore, it is there, near to my house, one is there. They are providing about 1,000 lines. Whereas a satellite can give 1,000 into 1,000. That many connections it can give one satellite. So we have got about 6, 7 satellites. That's what is operating giving all this connectivity. This WhatsApp and all do not have come otherwise. See, without our own satellites and other things, you cannot have so much of data coming, so much internet, so much facilities, 4G, 5G, NG also will come, future. So many Gs are coming. G means grading, up, 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 it's going. Images, other things, anything you can send. And you can even do, see, for example, now I am talking, and you can correct my slide. That level it will come in the future, a little later. So all these things are the very important thing. Next one, I'll tell you how the communication works actually. Next. So here the satellite is there. There's got an antenna, and there below also you can see antennas. And by increasing the antenna size in the earth, my communication becomes more and more. More power I am sending, I can get back more power. So for example, when I make a phone call to my daughter in USA, what I'm actually doing, it goes to my exchange here, Bangalore, and straight away it is going to satellite. Just detected that it's a detected that call to be a US call, overseas office it goes. From there, satellite to satellite jumping, and they're down. And within about same time, whatever time it takes for me to call you here, I can talk to my US people also. So basically, satellites are the link, long link which is provided. And of course, defense, I don't have to tell you, so many secret information, other things, they have to talk, they have to send messages, they have to send photographs, pictures, what is happening, everything that can also be done by encryption. They do big encryption, nobody can, every day it changes, every hour it changes. Who can find out all those things? So that is being used, and we have made satellites only for our defense. And they are not in the picture. You cannot get data from anywhere about that. Because that is meant for them, we made and gave to them. That's all. So that technologies are also there. Next one. So these are the basic things. You can see this infrastructure, which is now you can see how a satellite can communicate with so many things, and what is called as a VSAT. VSAT is a very small aperture terminal. I can make the aperture so small, like my soap box. That's a soap box. This where it is required is one for news collecting. People are going, something is happening. Somebody is telling I am changing my party from this to that. Immediately they have to pass it to the TV. So they use that soap box thing. In their car only it is there. They keep on the top of the car and they are transmitting. That data goes to the news office. There they give to the TV. Within no time, and matches you are seeing cricket match going on. They are all by this method only. VSATs. And third thing is business information. Lot of business exchange and all that. The data is very large data, and that's also being exchanged. So these are mainly for industry and defense and data public information and all that. Next one. Yeah. So, and this is one of the very, very wonderful things. It's going to change the life of everybody. Change the life of everybody. Already it's changing. GPS, all of us have heard of this global positioning system. What is that? Basically, basic physics, I am telling you. Basic physics. Pythagoras theorem. That's all. Pythagoras theorem tells what? If I know 2 points, the third point I can find out with some angle. Isn't it? Same thing. 20 satellites are there. They are going around. At any point from anywhere, you can see 3 satellites. Minimum. Out of the 20, even 4 also you will get. Then your accuracy will be even more. Using a simple basic calculation, they give you the position of yourself in their system. Their system, you are at so and so point. Now you see the GPS, how much we are using for navigation. All planes are using this. All cars are using taxis, trains, everything. Now, children also, now in USA and all, they give a small code, this thing like that, watch-like thing. If the child is lost, immediately they know the GPS, that number they put, where that fellow is there, where he has run. All these things are found out. And all the animals are GPS coded actually. Now, the wildlife and all that. And more than all these things, even you are traveling itself, some accident happens, something, and everything. Basically, GPS is going to be the geography and the communication together is going to be a big future of this thing. In fact, one example I will give you what is happening already in US and all. Very old people having some problems, like, they have a heart attack problem or some other thing, pulse goes down fast. What happened, they are having the GPS-based measuring system, and the moment that pulse goes down, immediately a message goes to the doctor actually. And no point the doctor gets a message, but where that the patient is there, you should know. GPS data also is given. Location also given. Immediately sends a person and saves that. This I have seen. Very old people, they are just putting this and then going. So people with some disease, some problems, alert requirement, all these things, in future. And I am thinking of the mobile itself, a big technology change is happening. So mobile is ultimately integrating all these things. Now GPS is already there, navigation we are using, but health has not been put there. Health is still not there. You have got smartwatch and all, you know that, but they have to integrate that also into the mobile. See, mobile, you just keep on your skin, it can measure. It is going to happen shortly. The pulse rate, everything, continuous monitoring will be possible in the future mobiles, where a health system also will be established. Weather, health, navigation, then temperature and other things, your food, even it will tell, come on, go to the nearest hotel and take food. And it will show you where it is, vegetarian hotel, where it is. Nowadays it's showing, no, exactly. You can select from so and so places where to go. So GPS is going to be the real future front runner with, of course, satellite integration and other. Next one. Yeah, here only, next one only, I'll show you how difficult it was for us to communicate with the moon. Moon is about 2.75 lakh kilometers away. You know very well, even little distance, the signal getting problem and all that. Then how you communicated with that and you managed that? Even now that, our first Chandrayaan 1 and 2 are still rotating. We are getting data every day. Chandrayaan 3, that rover has worked for some time, then stopped. But how you will communicate with a rover which is on the moon surface? It's only a signal. So how to get the signal? This aperture, this is actually 18 meter. You see here the terminal, which is the second one in the world. There is only one more in USA. That's all. Nobody else. So we are actually supporting many of the other people's mission, like Japanese and all. By using this terminal, we get data and send to them over land. We are getting their data. 32 meter. You have to go there and see. It's very interesting. Dodda Alamara, that's the name of the place. Yeah. There you can just travel and sometimes take a picnic. Now, after a day you go there, they'll show you everything. So this is one of the big achievements. Now here I want to bring down one point to you. Just a point. It's a little critic point I want to say. US said that they landed in moon around 1972. But where is that antenna? How they communicated with Armstrong? How Armstrong's voice we heard? These are all very doubtful things. Okay, I'm just putting in your mind that one. Next one. Because these technologies come now only. How they can communicate with the moon at that time. Now we are going to entirely different thing. Remote sensing part, you know how this communication, how successful it has been. Now the person who comes to your house for doing work, she is having a mobile. Sometimes two also. She is having even two mobiles. Mobiles have become like almost like so cheap, not cheap actually, available, plenty. See how it solved the big problem of communication in our country. Big problem. Second thing now we are talking about is a satellite with network. With this one. We want to have a satellite where internet it can provide. So we are actually working on that internet satellite. Once that comes, all our villages will have internet. Now villages do have some tower and all that. It's very costly affair. We have to have a tower for so many houses like that. But once a satellite internet comes, it can handle many number of connections, and always all networks will not be working now. So we have to work out how much basic number should be there. So we are working on that. In another year or so, we are going to launch satellite only for internet satellite. With that communication part, I'll stop here and now come to the satellite remote sensing. Let us just define the word remote sensing. What is that? We are all doing every day. See, once I open my eyes, I am doing remote sensing only. Very complicated thing happening in our brain. Let me tell you. Basically, I am receiving some signals. They are all electromagnetic signals. Being physicists, you all know that. Just got all the bands, starting from X-ray and all that, microwave and all, descent up to the meter waves. Everything is there. Visual waves are there, thermal are there, ultraviolet, infrared, everything is there. So what our eye can see is only 0.5 to 0.7 micrometer, only visible. It's not designed for anything else. So that is a basic principle we use in satellite also. But here what it does, that data goes and converted by the cornea into electrical signals, goes to the brain, and brain is already trained. If this looks like this, it's a dog. Looks like this, chair. Like that, we are able to. Same thing happens with satellite also. Satellite is able to see the signals, the ultraviolet, infrared. Only difference between the satellite remote sensing and our remote sensing is the satellite can see in all bands. See, for example, a big mountain you are seeing, when you're traveling in the bus, no, Andhra Pradesh. Particularly if you enter Andhra Pradesh, you'll see so many mountains with very big stones. We think of so horrible, so many big stones are there of no use. We have to only bring them down and break it and then use it for building. No, if you can see them in the X-ray microwave, they are all containing many minerals. These are all rock formations due to volcanism much early. So we need to study that. So now we have got satellites to do that. Basically, the geologists are looking at the satellite pictures in X-ray, microwave, infrared, ultraviolet. See, whatever I cannot see, the satellite can see that. And day and night also. So night time there is thermal picture. For example, I can see in the night with the satellite, but my eye I cannot see that. So what happens basically, satellite remote sensing is much broader than what with eye we can see. Second thing is what is called as resolution. See, what's the minimum size of an object which I can see? In the earlier times, 30 meters and all were there. Now we have moved to 1 meter and better than that. I'll show you with some images. These are different applications, forest, agriculture and all that. Next one. Next slide, sir. Yeah. Here, this is a very simple picture you can see here of Gujarat. In Gujarat, what is the main agriculture is oilseed, groundnut. They are very famous for agriculture. It's the best groundnut available in the world actually because of the heat and other things, conditions. But here you can see a picture of taken from our satellite. Not very high resolution, I'd say, maybe 5 meters like that. But you can see all the agriculture fields. And interestingly, you can also see some of them are having agriculture, some are not having. You are able to see, no? Some are white actually, they are not having any crop. Some are having crop with more red color. This red color is indication of IR. Actually, all plants are radiating both in red and IR also. So satellite picks up the IR signal. Red means better. So here you can see how varying it is, these things. So what Gujarat government did, they took an undertaking with ISRO. We had a big project there, how to improve the oilseed production. So we started going, not we, I mean the Gujarat, they found teams, they went to these places, found out why some of the fields are so big, but they are not having any crop. And they found very simple reasons, like they don't have seed, sometimes they didn't get money, sometimes they didn't get the little water to start with. Once it starts, the groundnut will grow, even in heat conditions. Like that, they could find out, and they solved all those problems. Their agriculture system totally got revamped, and we have increased the production by 10 times. Now they are exporting groundnut. You just think about that, a simple technology. All these fields, now I don't have a recent picture of Gujarat, I would have shown you. It is wonderful.